Hello, in this video I'm going to talk about representations of waves. We want to be able to draw graphs of waves, analyze waves mathematically, so we need some kind of equation, and it's nice to have other kind of diagrams and things like that just so we can see what's going on and communicate that to other people. Now, the difficulty we've got with these representations of waves and why we end up with having a few ways to do it is, well, let's come back to our lake with the disturbance and then the ripples coming out. And you think, okay, I want to say what's going on with this wave. Well, if you want to say, say I asked you, well, what displacement have I got on the wave? I mean, that's obviously something that you can't answer unless, because you'll probably respond and say, well, where in the lake and when? Because the wave is propagating through time and space. So we need answers for both of these things. So when it comes to something like a displacement, if we were going to draw a graph where y is our displacement, that is a function of position and of time. Now, usually, I mean, up until now anyway, in the relatively simple stuff that we've been doing, we've just got y as a function of x, or maybe y as a function of time. We don't have both. We haven't got these two variables kicking around. But that's what we've got here when it comes to displacement, because the wave is moving through space and time. So we can't draw animations. This is why you'll get so many things. You look them up on the internet and you'll find people have done wave animations where they got a gif of something where the wave is actually moving and you see how it's changing through time. Well, we can't draw that for obvious reasons on a bit of paper. So we've got a range of ways of drawing things out. Now, our wave profile is the first one of these. This is where we're looking as y as a function of x for a fixed time. So let's say, okay, let's freeze the wave in time and see how the displacement of the wave is varying through space. So we've got displacement on our y-axis, and then we'll have our x-axis being distance. So yeah, displacement versus distance. Now this will, in the case of a transverse wave, look pretty similar to the actual shape of the wave. So say the initial point, the initial disturbance point is now back at equilibrium, say, then we'd have something that might look like this. We're drawing a sine wave in, and these are meant to be all having constant amplitude here, an A and a minus A. We can read the amplitude off straight away. It's not decaying in any particular way. These are all at the same point here, and the same at the top as well. So we can read our amplitude off, we can read our wavelength off as being the distance between consecutive points at the same phase. So consecutive maxima, consecutive minima, that sort of thing, that's giving us our wavelength. But this is just at a snapshot in time. If we went to 1 second later on, everything would have moved because the wave is moving in that direction with the wave speed v. So we've got this changing all the time. If you drew it at a later point, well, what's going to be happening? This is moving, some fraction later. If you think of this going back this way, we continue the wave going on back to negative distance. Well, this is now going to be dropping down. So we're going to get the wave moving off to the side, and everything's just going to be slightly off, and the wave has moved along. So you can see now that what we had as a maximum here is now a maximum here. It's moved along by a certain amount based on the wave speed. So that's what people are then animating when they do these GIFs. But if we're just drawing out a wave profile, displacement with distance, we have to fix the time. So we'd say for the first one, I don't know, this is t equals 0. We might do for the next one t equals 1 for seconds. So that's one way of drawing out a representation of a wave. Another way is saying, right, well, let's fix a particular point in space and then vary the time. So we'll now take y as a function of time and we'll fix the point in space. So we fixed x. So this might be looking at, well, what's happening for the displacement at the point right in the center here. So we've now got displacement against time rather than distance, because we've fixed the position and we're just seeing how things change with time. Now we might get, I mean, it might end up looking more or less the same thing. I mean, we know we're starting off here with, say we were taking this bit here at time t is 0. We're saying, well, there's no displacement. Well, let's just draw in, you're going to get more or less the same shape. Okay, really wonky sine wave. You're going to get the same shape, you're going to have the same amplitudes, but now we're getting this time here, that's not going to be the wavelength going from points of the same phase. This is going to be the period. That is going to be our period of oscillation t. So we're just flicking backwards and forwards between, well, are we looking at the variation through space at a particular time, or the variation through time at a particular point in space? Right, a couple of things that can confuse people with these is, right, the shape of the graph isn't necessarily the same as the shape of the wave. Now, I mentioned this before with this wave profile here. You know, people look at these, oh, displacement with distance, this is the shape of the ripples on the pond that we've just drawn out here. And you say, okay, well, it is, in this case, it's a transverse graph. You know, that is going to be one and the same, really, when we're looking at these mechanical waves. That is what we're drawing out, is the shape of the wave. But of course, we've also got longitudinal waves. Now, here we've got our displacement. We're necessarily drawing off perpendicular to the direction of motion of the wave. Now, we can still represent a longitudinal wave in this way as a wave profile, but you have to remember that if we've drawn a longitudinal wave with one of these wave profiles, that doesn't mean to say that the particle is actually moving in a perpendicular direction. It's just a graphical way of representing the displacement versus the distance. It's not saying that the particle is necessarily moving in that perpendicular direction. So you need to keep it clear in your own mind that, you know, you get exam questions where they'll present you one of these graphs, and it's so easy to think, oh yeah, it must be a transverse wave. But it isn't. It's just a graphical representation of a wave which may or may not be transverse. So make sure you don't get caught up with that. I'll be doing some questions specifically that try to catch people out with it, or maybe they don't try to catch people out, they just do catch people out with it. So you want to make sure you're clear on that. And then we've also got the direction of the oscillator. It's easy to think about, oh yeah, well, what's happening? We've got some oscillator at this point here. You know, so it's at the 0 distance point. It's at the center of the ripples. What direction is it moving in? It's very easy to think, oh yeah, well, the wave is moving off to the right, that this oscillator is somehow zooming along the wave off to the right here. So you say, okay, what direction is this point here on the wave going to move next? People are, oh, it's going up, because moving that way in the direction of the wave is going upwards. But remember, these particles aren't moving along the wave. They are moving about their oscillation point. So what direction are they going to be moving in? Well, it depends what's coming up on the wave. This is the bit of wave that's coming up. The peak has already passed. The peak is off. The peak is heading off into the distance. The thing that's coming up to this point, because the wave, I've drawn it the way I've drawn it here, the wave is moving left to right. Well, the thing that's coming up is a trough. So this point here is going to be moving downwards, because it's this bit of the wave here which is about to hit it. So the peak's already gone. It's now moving downwards. So these are two things which are very easy to get confused with wave profiles, and something that we'll go through quite a bit when we're going through the exam questions and such like. So that's two ways, the graphical ways of representing waves, but we've got other ways as well of dealing with this. So we have these things, wave fronts, and we draw this sort of stuff out quite a lot. In fact, the ripple in the pond is a great example. So when we have this middle point and we start drawing these circles around, I'll try drawing them a little bit neater than my usual rough way of doing it. what are we representing here with these circles? And I mean, that does look like a ripple on a pond, which is why it's a good way to start with a pond example. So we draw the ripple on the pond like this because these are our peaks. So if we're saying, okay, every one of these lines is the maximum, if we were drawing our wave profile, so we've got this sort of thing, and every time we've hit one of these maximums, we're drawing a line on here. So these lines are what we're calling wave fronts. And the distance between each wave front is going to be a wavelength. And this is just an easier way of drawing this now over multiple dimensions. Yeah, these graphs, we're really drawing quite one-dimensionally. We're not being able to get this, well, in this case, a two-dimensional view of what's going on. So you'll get this as well with, like, say we're talking about a sound wave. It's quite nice to have, if you've got a wave traveling across the room, say. So we got a wave moving, well, through three-dimensional space, but at least we can draw wave fronts in two-dimensional space. So sound is moving along this way. Well, I mean, it could be light. I just happen to pick sound in this case. And we say, so what are these wave fronts representing? So these could be our high pressure points. Remember, our sound waves, these are pressure variations. So if these are all our high pressures, we've got the low pressure in between. Then every time we've got high pressure, again, we've got a wavelength. And we're just using these wave fronts to describe these maximum points on the wave as it progresses through space. We could do this with any wave, but it makes it easier to then say, as we will do in future videos, okay, what if we now hit a wall with a gap in it? So we've got some kind of solid wall, but we've got this gap in the wall. What happens when the wave starts hitting the wall, and what happens to the wave as it goes through the gap? And this is where we start getting onto diffraction. So the thing, again, you need to be clear with on these particular representations with the wave fronts is that the wavelength is the distance, is the gap between the wave fronts. It's not the length of the line that we've drawn. So it's not that, it's these gaps, because the gaps, that is the distance between consecutive maxima that we're drawing on these wave fronts. Right, so wavefront is another really good way of representing waves, and it opens the door to something else that we need to talk about in a later video, and I'll get onto this because it is it's quite an interesting way of dealing with waves. But of course, here we're looking at this is very directional. This wave, it's just, we've got this parallel beam where everything is just what we call collimated. It's all moving just in one direction. It's not spreading out in the way that this ripple on the pond is, where it's going in all these different directions. I mean, the natural state of affairs for a completely unhindered, unobstructed disturbance in space is it's going to spread out in all dimensions. It's going to spread out in 3 dimensions, but we have ways of constraining that wave. You know, we've already seen it with a pond. It's constrained to 2 dimensions because that's the surface of the medium that the wave is propagating on. The guitar string, that's constrained to 1 dimension because of the medium that's propagating, in which case the string. So, but you can get directional waves even inside a particular medium. You know, we can get cases where, you know, if you've got light just moving in 1 direction, well, you know, can we do that? How can we collimate it into a beam rather than just having it moving in all directions? You know, what's going on there? Same with sound. How can you focus sound? Now, I mean, we know we can do it in some fashion. I mean, if someone talks through a megaphone, then, you know, you get your ears blasted to pieces if you're right next to it. But if you're standing over here, well, you don't, even though you might be pretty much the same distance away. So we do have ways of making things directional, and that is something we'll get to in later videos. But in terms of this, of drawing things with wave fronts, this is what we're drawing with these lines. Just make sure you know what bit is the wavelength out of all of this. Right, next up in wave representations, we got rays, and these are the things that we draw all the time when we're, I don't know, showing how light goes through a lens or bounces off a mirror or something like that. So rather than drawing things with wave fronts, which, as we've just seen, is one way of showing how a wave is moving through space, we instead just draw straight lines, because we start hitting boundaries and things, and these wavefront pictures start getting a bit messy. So say we've got some mirror, we've got a flat surface, we've got a light source, then we just draw a line coming in. This is a ray with an arrow on it showing, well, we got light coming that way, it hits the mirror, and then it bounces off. It's showing the path of a ray. So what we're meaning by a ray, let's compare this to, say we had the mirror and we were doing this with wavefronts. So we'd be drawing in these wavefronts, and it just starts making the picture a bit messy and quite hard to draw, because it's going to be coming down, it's going to be hitting the mirror at some point, and then it's going to be, reflecting upwards like this to get the new wavefront coming off the other way. So you can draw it that way. I mean, as you can see, it's already a lot more difficult to draw than just having these straight lines. And you start getting all of this sort of hatch checker region down here where the wavefronts are overlapping and all the rest of it. It ends up being a bit of a mess. So it's a lot easier to say, right, well, if we've got a whole load of wavefronts, we can draw a ray which is just going perpendicularly through all of these wavefronts. So if these are all perpendicular, then great, we can just draw a straight line and then treat that as being the wave. Okay, it doesn't give us the information about the wavelength and things that we've got on the wavefront, being the difference between the distance between the lines, but it just makes it easier. If we're more interested in the path of the wave, then we draw these ray diagrams. So you get the same thing with refraction. A ray will come down, it will hit a junction, a boundary, between two different materials, and then the direction will change. So you get this change in angle from the normal as you're moving from the lower density to the higher density medium. So we draw these when we're looking for a change in direction. Really, it's just so much easier to draw a ray. There's not really much more to say about that. I suppose you'll see them in these lens diagrams where you'll have these parallel rays. Sometimes we do draw multiple rays coming in, such as when we're doing a lens ray diagram, because we want to see where everything's going. We'll have the same on mirrors as well. I'm going to do a separate video on ray diagrams, but we've got multiple rays coming in here, and then one in the middle goes straight through, these ones refract down, and then you get your image appear. This is how the lens is operating. So the rays, it's just a different way of presenting it depending on what it is that we're actually looking at. But do we want to look at the patterns? It's quite hard to draw something like diffraction, the spreading out, if you're doing it in terms of rays, where it doesn't really work. You've got a ray going through, and then you're going to have another one which is doing this. It ends up being a bit messy when we're looking at something like diffraction, because really with a diffraction, it's easier to visualize with wavefronts. We've got these wavefronts approaching, and then they spread out in a circular pattern on the other side of the gap. So it's horses for courses on these sort of things. Do you want to draw a wavefront diagram for the propagation, or do you want to draw a ray diagram for the propagation? It doesn't really matter too much. You can draw any of these for any of them really, but there's some that's just easier to do than others. Usually with reflection and refraction, we're going to do rays. For diffraction, we're going to do ray fronts. Just different ways of visualizing things. Right, the last bit in terms of representation of waves is when we're getting into the mathematical part of this. So as I've been saying time and again in these early videos, we're modeling a lot of this stuff as simple harmonic motion, or at least as harmonic motion, where the harmonic is sine waves. So we're taking these sine waves, and that's what we're drawing out, and we're essentially doing transformations on these. We know how to draw a basic sine wave, so we draw that out. Okay, great. But if we're just drawing your standard sine wave, it's going between 1 and -1. It's crossing the axis here at pi, 2 pi, etc., etc. Every pi, we've got another point of intersection. Well, not all waves look like this. We want to change the amplitude. So we want to be able to change this 1 and this -1. We want to change these intersections, because it could be, if we're looking at distance on the x-axis, we want to set this up so that's our wavelength. If it's time on the x-axis, we want to set that up so it's our period. So we're wanting to do another transformation of the graph here. We might not want the equilibrium point to be at 0. We might want to shift the whole thing up. We might want to shift the whole thing down. We might not want it to start at 0, 0. We might want to shift it right or left. So it could be that we're thinking, okay, actually the wave that we want to model, if we draw out our axes, and we might want this going backwards and forwards in time, we might say, okay, well, the equilibrium point, actually, we want to be up here, not at y is 0. We want to have different amplitude going on. That might be, I don't know, 3. We might want to say, well, our amplitude is going to be 2, so we want it to vary between 5 and 1, so we've got an amplitude of 2. We might not want it to start at equilibrium. We might want to start at some point here, maybe 4. And we might want to say this was a distance one, that we want to have a wavelength of 1 meter, in which case, going from here, we're going to need to get back to that point. So say it was going upwards and then downwards and then upwards again. So we've got this. We want to say, okay, by the time we've returned to where we started, we want that there to be 1 meter. So this needs to be at 1. So we've done a whole load of transformations here. We're no longer going through 0, 0 at the start. We've no longer going between 1 and -1. We've no longer got this wavelength or period being 2 pi. All of this stuff has changed. So this is what 4 of the transformations that we cover in A-level maths. Now we're not doing the reflection ones. So let's start with y as a function of x. So it's y varying with distance for fixed time. Let's just go with that for starters. And let's see what you need to do in order to produce, say, this graph down the bottom. So our basic sine wave, we've just got sine x. I'm going to space it all out a bit because I'm going to add in all the transformations. So say we've started with our basic y equals sine x. Right, there's a whole load of things we want to do. Let's deal with the stuff in the y direction first of all. We want to increase the amplitude from 1 to 2 because we're now going 3 up to 5 and then 3 down to 1. So the amplitude is 2. That's a stretch in the y direction times 2. So we multiply it all by 2. That gives us our y stretch. We also want to shift everything up 3 because the equilibrium position is now at 3. It's not at 0 for y. So we need to do a translation in the y direction by +3. So we add 3 on the end. So that's dealt with our y transformations already. We've now got to do 2 transformations in the x direction, which are the ones that people find more difficult. We need to rescale the x-axis so that we've now got a wavelength of 1. Now that means that we're going to have to, because remember, if you multiply, so if I multiply x by 2 pi, that is doing a stretch of 1 over 2 pi in the x direction. Recall, that's how your transformations work. So we'll be taking our wavelength of 2 pi, multiplying it by 1 over 2 pi to get a wavelength of 1. Another way of thinking about this is, say we had just done that transformation and nothing else. Then we can say, well, when x is 0, we'd have sine of 0. So that's fine. So when x is 0, y is 0. If x is then equal to 1, in this case, then we're going to have sine of 2 pi. Y is 0. It's back where it started. We've now created that wavelength of 1. Whereas if the 2 pi wasn't there, we would have to have 0 and 2 pi in order to get back to y is 0 and y is 0. So we've switched our wavelength from 2 pi to 1 by putting in this factor here of 2 pi. So that's dealt with our stretch in the x direction. Now we need to do a translation in the x direction because we're not starting at our equilibrium point. We're starting here at 4. So, okay, this is a sine wave, so we're halfway up. That means that's the equivalent of doing a sine 30 degrees on it, and to get halfway up, if you think about it. So that's 30 degrees, pi by 6. We're doing a shift in the x direction of a pi by 6 off to the left. So if we add on pi by 6, then we're going to be shifting over to the left-hand side, and we're going to end up getting this wave that we wanted. So the general format that we've got here, y as a function of x, is going to be a sine kx plus phi plus c. And these have got all our transformations in. This is our amplitude. This is our offset of our equilibrium position. This is our phase, because you're thinking that's how far we are through the cycle. So that's why we're using a phi there. It's talking about our phase that we spoke about in the previous video. And then we've got this k here, which is going to have something to do with the frequency or the wavelength, depending on whether we're looking at our wave profile or oscillator profile. So we've got all of that happening. If we want to set this graph in motion, we've got this snapshot here. We've said we've got y as a function of x for fixed time. Well, if we want to set this in motion, all we're doing is having a time variable phase shift. If our translation left and right here that we did, which was our phase shift, our phi that we've added in here, if that translation varies with time, then the wave will be set in motion. So if we just slip a t in here, now we've got a wave that's moving. We've now got y as being a function of x and t. The wave is moving, and that's great. It's moving through space. Brilliant. So then we get our two-dimensional description here of what the wave looks like. So that's where we're kind of pushing the boundaries now of how we're describing these waves. Now, there are loads of ways of describing waves. When you get on to much more advanced university level description of waves, we start getting into these differential equations and partial differential equations describing how the waves are described through space. Obviously, that's beyond what we're doing here, but at least we're taking a step towards it, of thinking how we can describe these sort of things. So there you go. That's 3 different ways of describing waves. We've got the graphical descriptions, we've got our wavefront descriptions, and we've got our mathematical descriptions of transforming sine waves. And we'll be looking at all of these in our practice questions and as we're going through all of the other topics in waves and optics.